Okay, so we're going to define something new, which is what we call a moment. So this is not just like a moment in time. In physics, a moment is literally the turning effect of a force. Okay, so please make sure you've got that definition. Okay, how can you identify the pivot in any situation involving moments? Well, it is the point that doesn't move. Okay, so for example, it could be the hinge on a door, or it could be literally that point, in a swing where that wooden platform literally goes up and down either side of that pivot. Okay, right. Again, as I said, situations involving moments, windscreen wipers. Okay, clocks, doors opening, opening the tins of paint. Seesaws, as I've mentioned already. So let's define the moment equation. Well, it's going to be the distance that will be, okay, from the pivot to the force acting 90 degrees, okay, to that distance. Okay, so it's the distance from the pivot to the force where the force acts 90 degrees to that distance. Okay. So we can see from this diagram, it's not the 50 centimeters or the 30 centimeters, it's going to be this distance here. Okay, so it's the distance between the pivot and the force acting 90 degrees to that pivot. Okay, so what does normal mean? Well, it means it's right angles to it. Which of these distances is normal to the force? 40 centimeters, as I've mentioned. Calculate the moment of this force. Well, it's going to be 120 newtons, okay, which is our force, times the distance normal to the force, okay, which is 40 centimeters. That's going to give us 4,800 nanocentimeters, or 48 nanometers. Now, why are moments important? So it's actually quite useful, okay, and we need to know this principle. Which states that the principle of moments states that for a balanced object, the total clockwise moments, okay, so that's this turning effect here, has to equal the total anti-clockwise moments, okay, so that's this turning effect here, okay. So let's have a look at the moment of the person on the left. Well, it's going to be their force, 400 newtons downwards, their weight, multiplied again the distance from the pivot to where the force acts 90 degrees to it, or where it's normal to it. So weight is obviously going downwards, so it is 90 degrees, so it's going to be 400 times 1.5, which is 600 nanometers. Okay, the moment of the person on the right, therefore, has to also equal 600 nanometers, which means we can work out this distance here. So it's going to be 600 times some unknown has to equal 600. Well, 600 divided by 300 is equal to 2 meters. So this person is 2 meters away from the pivot. Right, let's have a look at this next example. So again, we've got two people on this seesaw. This person's 300 newtons, they're 2 meters away from the pivot, but we've also got the mass of the plank, or the weight of the plank, which is 270 newtons. So the center of mass is slightly off center to the right, and it's a distance of 0.25 meters from the pivot. So we're going to work out the total anti-clockwise moment. First of all, so it's going to be 300 newtons times 2, which gives us 600 newton meters, plus 270 newtons times 0.25 meters, which gives us 67.5 newton meters. We add them together, we get 667.5 newton meters. So that's a total clockwise moment. We're now going to say that that total clockwise moment, because these two guys are in equilibrium, that means the anti-clockwise moment has also got to equal 667.5 newton meters, which means some unknown weight of this person multiplied by the known 1.5 meters to the distance of the pivot has to equal 667.5 newton meters. We rearrange that, so divide by 1.5, we get 445 newtons. So this person weighs 445 newtons. So for your exam, these are the sort of questions they could ask you. They could ask you the distance a person is from the pivot, or the weight. So you've got to be able to use this principle which states that the total clockwise moments has to equal the total anti-clockwise moments if the object is balanced, okay? Right, we're now going to be looking at levers. So levers are simple machines or devices that use the principle of moments. So in a lever, what is the effort? Well, it is the force that you put in. In a lever system, what is the load? Well, it's the force that you want to create. Okay, so let's look at this in a bit more detail. So levers reduce the force that we need to put in because the effort force is a large distance from the pivot. Okay, so hopefully from everyday experience you know this to be the case. Okay, so the fact that you open up doors the furthest away, or your door handle is the furthest away from the hinge, is because of this effect. Okay, so you put the least amount of effort so that you create a large load. Okay, this produces an equal moment on the other side of the pivot, but since the distance is smaller, it makes the load force bigger. Okay, so essentially we're using the principle of moments again. We're using this equation here, force times distance. If we're increasing our distance, that means the force we apply is going to be lessened, but the turning effect is still going to be the same. Okay. Okay, so it says explain which of these levers is the best to use for lifting the rock. Well, we've already stated this. The load is closest to the pivot in C, okay, which means that the distance from the pivot that the person has to actually push on is the greatest, which means the less force he's going to actually exert onto this lever here. Okay. And finally, we're now going to be looking at gears. So what we've got here, we've got a driver gear which is connected up to a motor. So it's got 24 teeth. So you can count. You can pause the video and count them if you like. And then we've got this gear on the right hand side, okay, which is sometimes called the driven gear, and it's got 12 teeth. Now, when the gear on the left turns once, the one on the right will turn twice. Okay, it's from simple maths we can do this. It's just 24 divided by 12. Obviously, it's 2, which means this ensures that the actual speed of rotation speeds up. Okay, for the secondary gear here. Okay, the one on the right, which means we call this setup a speed multiplier. So let's look at this next gear system. So we've got 8 teeth on the left gear here. We've got 16 teeth on the right gear here, which means when the gear on the left turns once, the one on the right will turn half a turn. Okay, that's simply because it's twice as large. Okay, and obviously 16 divided by 8 is 2. Okay, and we call this setup a force multiplier. Okay, so that means for a more amount of rotations for the left gear, we're actually going to get a larger force being generated in the secondary gear. Okay, so it says give an example of a situation where a speed multiplier gear system would be needed. Well, that's simply increasing the speed of a wheel on a bicycle. Okay, if you're traveling on a flat level ground, if you have your gears arranged like this, means for every rotation that you do with the motion of your feet, the gear here is obviously going to go twice as fast, which means obviously your wheel is going to spin twice as fast compared to the rotation of your feet. Okay. When would a force multiplier be useful? Well, lifting a heavier object, of course. So obviously rotation. It doesn't matter if you rotate it quite quickly, the force that you need to rotate this gear here is actually less than the force that's going to be generated in this secondary gear here. Okay, so the same principle applies when you're going uphill, cycling up the hill. Again, you're going to rotate with your feet on this gear, and that's obviously going to spin at a faster pace than your wheel of your push bike. But at least it means that the force being generated is going to be an actual stronger force. Okay.